So in this lesson, we're going to apply properties of exponents to expressions with fractional exponents. Take a look at example 10. We're asked to simplify 2x raised to the 1/2 times 6x raised to the 5/2. Well, remember, we're going to kind of group here, right? We'll group the 2 and the 6. So 2 times 6 is 12. And then we have the same base, which is x. So we add the exponents. So 1/2 plus 5/2 is 6/2, which reduces to 3. So our final answer would be 12x cubed. Let's try a few practice problems and take a look at the rule. So in number 60, we have x to the 1/4 times x to the 1/4. And using properties of, multiplication, we have the same base. We add the exponents to get 2/4, which will reduce to 1/2. So our final answer is x to the 1/2. Let's take a look at number 62. I'm going to want to group the -2 and the 3, -3, to get +6. And then I'm going to add the exponents 7/8 and -3/8. So the -2 times -3 is +6. 7/8 plus -3/8 is 4/8, which reduces to 6 and 1/2. 6y to the 1/2. 64, well, we're going to divide the 8 and 2 to get 4. And then when we do division, we subtract exponents, right? Multiplication, we add the exponents. Division, we subtract exponents. So there's my 4 from the 8 divided by 2. 9/4 minus 3/4 will leave me with 6/4. And that will reduce to 3/2. So my final answer is 4y to the 3/2. Problem 66. So for problem 66, we have the -2 raised to the 4. So that's -2 times -2 times -2 times -2. We do that 4 times to get +16. Now the 2/3 we multiply by the 4, right? The product to a power rule says we multiply these two. So 2/3 times 4 is 8/3. So we're left with 16m to the 8/3. Now we're going to move on to scientific notation. Right? The book tells us, yes, when we have very large numbers, like the distance to the sun, 93 million miles, or very small numbers, such as 0.0005, the width of the fiber and fiber optic cable, sometimes it becomes cumbersome to write these big numbers out. So perhaps there's an easier way to express 93 million, or 0.00005. We can do that using scientific notation. So if you take a look at their example 13, I have 7.08 times 10 to the 3. Essentially, I'm going to move the decimal place 3 times to the right. So if I have 7.08, I can move the decimal 3 places to the right, and they have an equivalent answer. If I have a -3 as an exponent, I'll move the decimal place 3 places to the left. So 1.4 becomes 0.0014. All right. So there's some practice problems. All right, we look at number 68. We have 7.045 times 10 to the 6. So I'm going to want to move this decimal point 6 places to the right. So when I go 6 decimal places to the right, 1, 2, 3, 4, 5, 6, my new number is 7,045,000. And perhaps I should add the commas in. Number 70, see, since my exponent's negative, I'm going to go to the left, right? So if it's a positive exponent, we move the decimal to the right. Negative exponent, we move the decimal to the left. So 3.02 times 10 to the -3. If I go 3 decimal places to the left, 1, 2, 3, I'm left with 0.00302. Then they give us a definition down here, right? They say a number is in standard form if it's written in the usual decimal notation, right? So this 7,045,000, that's standard notation, right? This 0.00302, that's standard notation. Numbers in scientific notation form, if it's written as the product of a number between 1 and 0, including the 1, and an integer power of 10, right? So when you look at 68, right, the first number is between 1 and 10, and then we're multiplying that by 10 to some power, right? Some power of 10. So for practice, it says, is the given number in scientific notation explained? So when I look at 72, the answer is no, because my first digit is 0. And we're told that we have to be between 1 and 10, and we're allowed to include the 1. So number 72 is going to be no. So let's take a look at 74. Is the given number in scientific notation explained? And the answer is yes, because the first digit is between 1 and 10, including 1, right? So 1 qualifies. And it is a power of 10, right? 10 to the negative 7. So let's move on. Okay, it says to write numbers in scientific notation, place a decimal point so that there's exactly one non-digit 0 to its left. This is value A. Count the number of places you move the decimal point. This is the exponent without its sign. And to determine the sign of the exponent using the following. So let's take a look at example 14. It says write 3,297,000 in scientific notation. Right? So we're going to take the 3. That will be my first digit. And then how many decimal places do I move? Right? I say 1, 2, 3, 4, 5, 6. So it's 3.297 times 10 to the 6. Right? And since we went to the right, we know that the 6 is positive. When I look at example 15, I'm moving 1, 2, 3 decimal places, right? So this 0.0547 will be written as 5.47 times 10 to the, and then we have to ask ourselves, how many decimal places did we move? We went 1, 2, 3 decimal places to the right, so the exponent's going to be negative. So let's take a look at a few practice problems. We're told to write each number in scientific notation. So number 76, we have 0.074. So we're going to need to move the decimal 2 places to the right. So we have this 7.4 times 10 to the negative 2. And I use the negative 2 because we moved the decimal 2 places to the right. Let's take a look at number 78. We have 34.3 million people. So first I think we should write this out in standard form, the 34.3 million people. So 34.3 million people, if I write that in standard notation, that would be 34,300,000 people. And if I move my decimal 1, 2, 3, 4, 5, 6, 7 places to the left, we'll write 3.43 times 10 raised to the 7. Okay. See, the positive exponent has the effect of making this number bigger, this 3.43 bigger to the 34 million, and the negative exponent makes this number smaller, right? That gets us to that 0.074. If we take a look at number 80, the width of a human hair, all right, so we have 0.0009. So I have to move the decimal 1, 2, 3, 4 places to the right. So my answer should look something like this, right? 9 times 10 to the negative 4. Right? We move the decimal 1, 2, 3, 4 places to the right, so that's why we have a negative 4 here. Moving on, we have a few more practice problems. It says, write each number in standard notation. All right, so I have this 1.02, and it looks like since I have a negative 5, I'm going to move the decimal 5 places to the left. So here's my answer. Right, if I move my decimal 5 places to the left, right, 1, 2, 3, 4, 5, that looks like that works. For number 83, it says the U.S. daily Coca-Cola consumption, 5.24 times 10 to the 8 servings. It's a lot of Coca-Cola. We're going to move the decimal 8 places to the right, right? So if it was negative, we went to the left. Positive, we're going to go to the right. So it looks like we have 524 million servings. And again, I just want to make sure I did this correctly. So it's 10 to the 8. So if we go 1, 2, 3, 4, 5, 6, 7, 8, that lines up, right? We're moving the decimal 8 places to the right. Last one, number of cell phones tossed in the trash each year is 2.57 times 10 to the 7. So I'm going to move the decimal 7 places to the right. And it looks like my answer is going to be 25 million cell phones. Right? And again, if I move the decimal 7 places, 1, 2, 3, 4, 5, 6, 7, that looks like that lines up with the 2.5.